The GIT is metabolically significant size of SAA metabolism in the body and metabolizes about 20% of the dietary methionine intake, which is mainly transmylated to homocysteine and transsulfurated to cysteine. In vivo studies in young pigs indicate that the GIT is a site of net homocysteine release and thus may contribute to the homocysteinemia. The gut also utilizes 25% of the dietary cysteine intake, and the cysteine uptake by the gut represents about 65% of the first pass uptake. A study showed that SAA deficiency significantly suppressed intestinal mucosa growth, reduced intestinal epithelial cell proliferation, and increased intestinal oxidant stress in piglets. These findings indicate that intestinal metabolism of dietary methionine and cysteine is nutritionally important for intestinal mucosal growth. Cysteine is the rate-limiting amino acid for glutathione synthesis, the major cellular antioxidant in mammals.
Hi, I'm EZATY and I will discuss rules for metabolism of intestinal cysteine. There is research indicating that the cysteine provide an essential functional and metabolic significant impact on human health and disease. The potential of regional accessory cells to secrete cysteine critically influence the reactivity of T cell receptor of intestinal lamina propria T cells. Cysteine plays a vital role in cellular redox status by way of its thiol moiety, as well as cysteine acts as glutathione's precursor, which is a significant cellular antioxidant.
Cysteine synthesized endogenously mainly in the liver and to a lesser extent in gastrointestinal tract. Serine and methionine plays the role as the precursor for cysteine biosynthesis. Serine provides the carbon chain and nitrogen atom, while methionine provides the sulfur atom. Homocysteine metabolized by the GI tract from dietary methionine through transmethylation condensed with serine catalyzed by cystathionine beta synthase to form cystathionine. Cystathionine gamma lyase, also known as cystathionase, cleaves and breaks down cystathionine into cysteine and homoserine and further deaminate into alpha-ketobutyrate. The sulfur atom in the polypeptide chain of cysteine could form a bond together with another cysteine, namely as disulfide bridge by oxidation, forming cysteine.
Cysteine can be metabolized by two routes, which is the transamination pathway and the direct oxidative pathway. In direct oxidative pathway, cysteine will be oxidized with the help of cysteine deoxygenase enzyme and then converted to cysteine sulfonate. Cysteine sulfonate undergoes transamination reaction and gets converted to sulfate and pyruvate under desulfuration reaction. And then sulfate get converted to next active form, which is PAPS, which is phosphoadenosyl phosphosulfate. Back to cysteine sulfonate. Cysteine sulfonate undergoes decarboxylation reaction and there is removal of carbon dioxide as byproduct, which then converted to hypotaurine. Hypotaurine then oxidized to taurine, which is an inhibitory neurotransmitter. It is one of specialized products synthesized from cysteine through direct oxidative pathway.
In transamination pathway, cysteine undergoes transamination with the act of enzyme cysteine transaminase in the presence of alpha-ketoglutarate to form beta-mercaptopyruvate, and there is also synthesis of glutamate. Beta-mercaptopyruvate undergo desulfuration reaction with the help of sulfotransferase enzyme to synthesize pyruvate, and there is also synthesis of hydrogen sulfide. Hydrogen sulfide, with the help of reduced glutathione enzyme, which is a tripeptide, is converted into sulfide, then sulfide oxidized to sulfide, and sulfide oxidized to sulfate. Sulfate has two phases, which is it can either be converted into PAPS, which is phosphoadenosine phosphosulfate, or being excreted through urine.